All right, moving on to a new chapter. So if you kind of look in our schedule on the syllabus, it says we just finished the previous chapter, and this is the only section from this chapter that we're going to cover. And it seems like we skipped a chapter, but after this section, we're going to go back and cover that old chapter that we missed. So it seems like this section's kind of out of left field. It's like, why are we only going over one section from this chapter? It's kind of weird. Well, I think we go over it in this class because this chapter is more of a chapter for the next class you'll take in your next semester. But this is such a strange concept that it's good to have seen it early, and that way when you see it next semester, it'll be a lot less foreign and strange. It'll look a little more familiar, and it'll be easier to tackle. So this section, there is homework on this section and all that in this class, but we're not going to go too deep into the subject. It's just this one section, just an introduction, so that it'll be easier to kind of understand next semester. Anyway, then we'll move on to the previous chapter that we skipped on accident, and then that's more this class's material. All right, this section is completely new stuff. I mean, you might use a little bit of what you know before, but it's really completely new, very strange concept. So if it really doesn't make 100% of sense, it's kind of strange to you even after you do all the homework and you've watched the video and you're saying, man, this is weird. I don't get this. I think that's pretty normal. It's just kind of, like I said, it makes it easier the second time you learn it. I don't know, I guess the more times you're exposed to something really weird, the less weird it seems each time, I don't know if you ever have a friend or someone you know that's just really weird. The more times you're around them, you kind of get used to it and they're less weird every time and you just kind of accept them. I think that's what we're kind of trying to do in this section. I know that sounds silly. But let's see, let's look at the top of this page. It looks really strange. It's like, what, is this math? This doesn't even seem like math. We have 3 examples of what we call correspondences. So we got, first one, to each person in a town. Okay, so you picture a bunch of people in a town. To each person in that town, there corresponds a date of birth. Which makes sense, yeah, for every person in a town, of course they're going to have a date of birth, like November 3rd, 2012 or something, whatever it is. Something like that. And if you want to make it a little bit more math-like, you could say, okay, here's a set of people in a town, because those little squiggly brackets mean a set. The people in a town, they correspond to, or they have, you're sending an arrow to all their dates of birth. It's kind of a little bit more mathy way to say it. But it's still kind of the same thing. It's just more math. So that's kind of like your first example of a correspondence. Yeah, they call these guys correspondences. This is a correspondence. Yeah. All right, and then you got another example, just to kind of get a really wide variety of weird examples. To each barcode in a store, right, because each item has a barcode, there corresponds a price. Yeah, that makes sense. Every time you have a barcode, then you scan it, it's going to give you a price. All right, and you can write that in a more math kind of intensive way. The set of all barcodes in a store correspond to all the prices. Okay, that one sounds good. I believe that. And you can think of, if you kind of know the word correspondence from, just the English language, what does correspondence mean? It's kind of what you would think it would be. Corresponds to something. They're related in a way. And then the last one here we got, to each real number, all right, now we're getting more math-like, right? To each real number, there corresponds the square of that number. Okay, so I guess if you want to go even more fully in math, you could say, for each real number, let's say it's x, there corresponds the square of that number. That means you can raise it to the second power. All right, but in the kind of the set notation, you can say, to the set of real numbers, there corresponds the square of all the real numbers. If you take all the real numbers, you square them, and that'll send you from one set to the other. It's kind of these are weird examples, right? It's just kind of, if you have a set of things, they could be people, like in the first example, they could be barcodes, like in the second example, they could actually be numbers. So if you have a set of things, or people, or numbers, whatever they are, there's a correspondence. It means kind of like with this arrow, they're sent to something. Like the people, they're sent to their dates of birth. The barcodes in a store, they're really sent to their prices. Real numbers are sent to their squares. It's kind of a weird thing, but I'll try to introduce, more and more things here to make it more clear. So let's see, what are they saying here? So notice that in each of the above examples, we're going to have a new definition. This is going to be really important, especially next semester when you kind of delve deeper into this chapter. Okay, in the above examples, the first set is called the domain. So I always think of the domain as kind of like the starting point, you know? So all those left things that we had, like in the first example, it was the people in the town, they were the domain, because that's where you're starting. And then the range is where you're ending. So in that first example, the people in the town that was the domain, and the range, they were sent to their dates of birth. So the dates of birth are the range. In the second example, the barcodes in the store, that's the domain, because that's what you're starting with. And then they're sent to the prices, so the prices are the range. And then the last one, the real numbers on the left, those are the domain. And then the squares of the real numbers, those are the range, because that's where all the numbers are sent to. And these kind of correspondences are called functions. And we'll get deeper into what a function really means. There's a technical definition, and there's something that you really have to check to make sure it's actually a function or not. We'll talk about that later. But yeah, I would say think of a function as like a map. You're mapping one set to another. A map that sends elements of one set to another set. And I guess by elements I just mean the individual things in the first set. Yeah, and then the first set is the domain, and then the other set is the range. Domain, range. Yeah, so I think that's what I would say. Think of domain as your starting point, and then range as your ending point. Anyway, kind of strange. There's another way you can think of these correspondences, like in this picture here. It shows a correspondence. It shows the domain is on the left and the range is on the right. And notice that it has arrows. You'll kind of see that theme throughout. It's showing there's a bunch of numbers here in the domain. There's -4, there's -2, there's 0, and there's 3. And they're actually showing you where they're sent. They're saying, look, -4, he's being sent to -3 in the range. So he started at -4, is being sent to -3. The other guy in the domain, -2, he's being sent to 6 in the range. The 0 in the domain is being sent to +3 in the range. The 3 in the domain is being sent to both 5 and to 7 in the range. So it's kind of interesting. There's a correspondence. And we'll talk more about this correspondence when we have the technical definition of function. But right now it's just kind of notice that that's one way, kind of a visual way you can show a correspondence, actually showing exactly what each individual thing in the domain is sent to in the range. It's kind of a nice visual way to do it. Another way you could do it is, here's another correspondence to its right. They just give you a table of values. So one thing that we kind of want to get used to is that as we're trying to relate this idea of functions and domain and range, we're trying to relate it more to math. Because right now it's kind of abstract. We're going to think of the domain as x values and the range as y values. So that'll be a theme that you'll see, especially if you take higher math classes like pre-calculus, trigonometry, calculus. You really associate x values with domain and y values with range. So kind of like here, if you wanted to, you're thinking of like x in the domain is being sent to 0 for y in the range. 6 in the domain is being sent to 2 in the range. 7 is being sent to -3. 8 is being sent to 2. So it's kind of like a correspondence that we saw in the previous little visual example. It's just they're not giving us, I don't know, it's not as visual, it's more just a table of values. But really, you know what you can relate those to? The first thing they said, 5 in the domain, was sent to 0 in the range, but that's an x and a y value, so you can think of that as an ordered pair. The same for the second guy, 6x and 2y, 7 and -3, and then 8 and 2. So really that's just a bunch of ordered pairs. We're saying if you have an x value of this, it has a y value of that. You know, these x values correspond to these y values. But still, we can think of that as a correspondence. Alright, and the last example in this row here, it's just another correspondence, but it's getting a little more specific. So you notice at the top they say, okay, the left column is the x values, but in the right column is the y values, but they're giving us exactly how they got those y values. They're saying, oh, y is equal to some kind of, like this is the equation of some line, right? It's kind of like mx plus b, 2x plus 3. They're telling you exactly how they got the y values. You take this x value, say -3. If you were to plug that in here for x, it would be 2 times that plus 3. 2 times -3 plus 3, you'd get -3. So they're actually telling you where the y values are coming from. And then if you try -1, what if you put a -1 there for x? 2 times -1 plus 3 would be 1. That's where it's sent to. That's the y value. And on. If you put 0 in there, you're going to get 3. If you put 4 in there, you're going to get 11. So kind of interesting. This one's a little more specific than the last one because they're telling you where they're getting the y values. Whereas the last one, notice they just told you, hey, 5 is associated with 0. Don't ask me why, it just is. 6 is associated with 2, etc., etc. So interesting. All right, we'll come back to those examples once we have something more interesting to talk about. So below that, it actually gives you the definition of a function. What is it here? It says a function, it's a correspondence between a first set, so we kind of said that already, the domain, that's kind of like your starting point, and then a second set called the range, that's your ending point. But the thing that's really good to keep in mind is this part, that each member of the domain corresponds to exactly one member of the range. So that's the part that's going to be hard to make sure of, because not all correspondences are functions. And if someone asks you, is this a function or not, this is what you really have to check. Make sure that each member of the domain corresponds to exactly one member of the range. So kind of another way to think of it as would be, or the easier way to think of it, no element in the domain is sent to more than one element of the range. You know, so there's no way that one x value could be sent to two different y values. We don't want to see that. That's a bad thing. That's kind of hard to remember. I think it's hard to remember because a lot of people they will remember, okay, I know that one thing can't correspond to more than one thing in the other set. But sometimes people mix them up. They'll say, wait, was it only one thing in the domain can only be sent to one thing in the range, or was it like one thing in the range can only be coming from one thing in the domain? They kind of get them mixed up. But the way I remember it to see, what the definition is, I think of a function like an airport. I know that sounds crazy. I think of an airport, okay, where you have the set of passengers as the domain. So let's say passengers equals domain. All right, we can even think of like a visual here. Here's all the passengers in an airport. It's probably like a really slow day because there's only a couple people there. Here's one guy waiting for a flight. Here's another guy. Here's some other person. Maybe there's only 3 people or something, but so there's the domain. That's where your starting point. A bunch of people that are the passengers, and then you can think of the range here as the set of destinations. It's like the places they're trying to go. Range. All right. So let's say, I don't know. I'm making stuff up. How about China, Russia, Europe. I don't even know. Oh, Russia's in Europe. I should be more specific. I don't know. Italy, sure, why not? Mexico, why not? And there could be more, of course. I just can't really fit more than that in this little circle. So I mean, think about it. Could one guy, let's say this guy right here, could he go to China and Russia at the same time? No. He can buy 2 tickets if he wants. Like, I'm gonna buy a ticket to go to China and Russia at the same time. But he can only go one place at a time, He can only either go to China or Russia. It's a choice of his. That's kind of how I remember a function, that a thing in the domain can only go to one place in the range. How can one thing go to 2 different places at once? It doesn't make sense. So every person can only go to one place. But think about it the other way around. It could be possible that 2 people, let's say these bottom 2 people, they both go to the same place in the range. Like, what if the second guy is going to Italy, but also the third guy is going to Italy? Is that wrong? No, it's fine for 2 people to go to the same place. It just wouldn't make sense for one person to go to 2 different places. So that kind of just reminds me that it's okay for 2 elements in the domain to go to the same place in the range, but one domain element can't go to 2 different places in the range. That wouldn't make sense. Yeah, so I don't know why, but the airport thing makes it make sense to me. Like, 2 people can go to the same place, that's fine. but one person can't go to two different places. That doesn't make sense. So alright, let's see if that definition can be put into practice here. Let's see, example 1, after all that weird talk, they're asking, are the above examples of correspondences, they're talking about this diagram up here with the kind of ovals, and then also these tables to the right of it, are those functions, yes or no? So let me kind of label it, I guess. The first one, it looked like this, a bunch of arrows, da-da-da-da, just so we remember what it was. That guy, and then there's the first table, X, Y, da-da-da-da, okay, and then the very last table. I don't need to write it all out, but that way we kind of recognize what we're talking about. So how about the very left one, that correspondence? Is that going to be a function or not? Well, looking back at it up here, I guess what you're looking for is there any element of the domain that is mapped to two different things in the range? Because that would be bad. So that's what I'm really looking for, is there one element in the domain mapped to two or more even. If it's more than one, or more than two, that'd be even worse. Mapped to two different range elements. If the answer to that is a yes, that means that's bad. This is not a function. But if I see that all my domain elements are only sent to one place in the range, that means it is a function, it's a good guy. But if you look at this diagram here, where is he? This guy, notice that, 3, he's mapped to two different numbers, right? He goes to 5 and he goes to 7. That doesn't make sense. That's one passenger going to two different places on an airplane. So this guy must be not a function. Or, this guy is not a function, unfortunately. So really, yeah, when someone says, or someone asks you, is this a function or not? That's what you're looking for. Are there any x values, or are there any domain values that go to more than one place in the range? Because that would be bad. If you do see that, the answer is no. But if you don't see that, that means this is a good correspondence and it is a function. Let's try to look at that table, the table in the middle there, and see if we see the same thing. So okay, we got 5 is going to 0, that's fine. 6 is going to 2, okay. 7 is going to -3, and 8 is going to 2. That's fine, right? At first I got scared, I said, oh look, 2, I see 2 twice. But remember, that just means there's 2 people at the airport, say 6 is one guy, and 8 is another guy. They're going to the same place. But that's okay, like 2 people going to Italy is not that weird. Usually planes are full, right? There's not just one person on each plane. So that's fine, this is still considered a function. It would only be bad if you saw, I don't know, like let's say, instead of an 8 down here, it was like a 6. Or no, not that one, sorry. Let's say instead of that, 7, let's say. 7 is going to -3, what if that was a 6? So this kind of second row here, they said 6 is going to 2, but the next row they said 6 is going to -3. That would be bad. That means one thing is going to two different places, and that's not what we want to see. But I don't see that happening. Every x value, or every domain value, is only going to one place in the range. There's no one x value going to two different places in the y value. So this is a function. It is a function. Alright. Let's try the next one. So the next one's the next table. Do I see any of the domain values going to two different range values? No, they're all unique, huh? You see, -3, he goes to -3. That's fine. He didn't go very far. -1 goes to 1. That's fine too. 0 goes to 3. Fine. 4 goes to 11. They never mentioned, I think the thing you'd be worried about is what if I saw -1 twice? What if there's one more row? So in the second row it said -1 was going to 1. And what if later on they said, well, -1's going to 6? Then you'd say, wait a second. On one hand you said -1's going one place, and now you're saying it's going somewhere else? No. That would be a bad thing, and that would be not a function. But since I don't see that, this is definitely a function. Because there's no such x value going to two different y values. Or there's no domain value going to two different range values. Same kind of idea. Alright, so that's a weird concept, right? Kind of strange. So we'll keep talking about whether something is a function or not, but looking at it through a different lens. Let's see, example 2 here, it's saying, are the following correspondences functions? So looking at part A, think of, like we said, think of these ordered pairs as x and y values. X, y, x, y. And remember that x values are the range. Or sorry, I mixed them up. X is the domain. X is domain, Y are the range. So you can actually, if you want to, draw your own arrows, like, okay, I guess if I'm thinking of correspondences, 0 is going to 4, because X is the domain value, 4 is the range value. But really, if you wanted to actually, if this kind of, the set of points is confusing, you can write a little table. Say, alright, what are my X values and Y values? The first one was 0, 4. So 0 is sent to 4. The second one, negative 2 is sent to 1. And the third one, 5 is sent to 8. The fourth one, 6 is sent to 4. And then the last one, negative 1 is sent to negative 19. Those are fine because I see that all the X values are unique. So there's no way that one X value is going to two different places because they only mention each X value once, right? So A, yes, it is a function. Because yeah, I don't see any X value mentioned twice. I don't see an X value going one place and going another at the same time. So that guy's fine. And then I think for part B, we don't really need to draw a table. I'm just going to think of it as 1 is going to negative 3, 5 is going to 4. Okay, so far so good. 6 is going to negative 2. Oh, this is not good. 5 is going to negative 5. Notice that the second ordered pair and the fourth ordered pair is saying 5 is going to two different places. 5 goes to 4, but at the same time, 5 is going to negative 5. That's one crazy passenger in the airport trying to go to two different places at once. Okay, crazy guy, that's not going to happen. So since that's a red flag, that means it's not a function. No. Not a function because one domain value is going to two different range values. Alright, so we kind of know if we're given a visual representation of a function, a visual representation of a correspondence, we know how to tell whether it's a function or not. The last type of way to say whether a correspondence is a function or not is, what if you're just given a graph? They're saying, so like, look at this top right example here. They're saying, here's an example, you got a bunch of points. There's like, how many points here? 7 points? 1, 2, 3, 4, 5, 6, 7. Is this a function or not? Well, if you wanted to, you could actually list all those points. You could say, okay, let's see the very top left one. He's negative 3 on the x-axis. What's he on the y-axis? 9, alright. There's 1 point. What's the other guy? The next guy, negative 2, 4. There's a second point. The third point is here, negative 1, 1. Okay. This lowest point is 0, 0, the origin. And the next guy is 1, 1. This other guy is 2, 4. And the very last guy in the top right corner is 3, 9. So now that I have it kind of listed in ordered pairs, it's easier to tell. Is there any x value that's going to two different y values? No, at first I got worried. I said, look it. Here it's negative 1 and 1. Here it's 1 and 1. They have the same y value. But remember, it's okay to have the same y value. It'd be bad if two different points had the same x value. Because this means, since the x values are different, negative 1 and 1, that's just two different passengers trying to go to the same place. So that's fine. This guy is a function, yes. It is a function. Yeah, okay. And if you think about it, okay, what you're looking for to see if something is a function or not, you're looking to see if, what is it? If one x value have two different y values. I guess that would be bad, because that's what you're looking for. If one x value had two different y values, then that means it's not a function. But if you think about a graph, when would that happen? When would one x value have two different y values? Well, that would mean those 2 points like above each other, say, like, I'm going to just draw a couple here, over here and over here, let's say. So if those were 2 points on your graph, what does that mean? That would mean you'd have 1 point, this is like 4, 2, and this is 4, 6. So notice those have the same x value but different y values. So really for a graph, what you're looking for is, are there any points directly above each other? You know, is there 1 point directly vertical from another one? Because that would be bad. And notice I just made those green ones up, but of the ones they gave me, these blue ones, none of them are directly above each other. They're all a little askew, you know. The second one here is to the right of the first one, so one's not above the other. And then they keep kind of progressively going right. But if one of them was directly above the other one, that would be bad. But that actually brings us to a way to tell whether a correspondence is a function if you're given the graph. So we get what they call, let's see, I'm going to write it over here actually, just to kind of have a place to write it. This one's called This is the test we'll use, the vertical line test. I don't know if you've heard of this before, maybe not. This is just kind of a quick way to tell if you're given a graph and they say, hey, check this guy out. Is he a function or not? This is a really quick way to tell without having to try to write out all the points like in the first example. Okay, so if it says if any possible vertical line intersects the graph at most once, it is a function. If it intersects more than once, it is not a function. There's kind of a quick way to tell whether a graph of a correspondence is representing a function. And it kind of comes from where we said. Remember what we said in the first example? We said what we'd be looking for, what would be bad is if 2 points were directly above each other. So what we do is we say, we're going to kind of take any vertical line that we can think of, like, I don't know, this guy. And if it happens to pass through 2 points at once like that, that's a bad thing. Because really, if you take a vertical line and it passes through 2 points, that means that there were 2 points on this graph that were directly above each other, which is what we were saying is the bad thing. Alright, so let's try it on this next example, the one to the right here. This is an infinite graph, because you notice that the arrow is going off to the right forever. So it actually wouldn't even be possible to write out all the points like we did in the last one. That would be impossible. There's infinitely many points on that graph. So really, I do have to use the vertical line test. So like it says, you're trying to think of, like it says, any possible vertical line. So I'm just picturing it. What if I draw a vertical line here? Does that go through the graph more than once? No, it only goes through once, right? There's only one place where it intersects. Okay, let me try another one. This vertical line? No, it goes through once. There's no vertical line, I don't think, that would ever intersect this graph more than once, right? There's no way. It's impossible, because this graph has no two points on it that are directly vertical from each other. They're all kind of curving off to the right, you know? So this guy, it is a function. It is a function. And that's because of the vertical line test. No vertical line will intersect this more than once. Graph more than once. Yeah, that'd be impossible. There's no way. Let's look at the bottom left example there. It's kind of like a sideways U shape. So that one I want to see if that's a function. So all I have to do is say, alright, let me think of any possible vertical line. Let's say this guy. Is that going to intersect the graph more than once? Yes, it does. Here and here. Twice. So really, all you have to do is think of, if you find one vertical line that intersects it more than once, that's already a bad sign, and that means it's not a function. This guy is not a function because there is a vertical line which intersects the graph more than once. So we found one, so that means it's a no. So it's really it's a lot easier to prove something is not a function, because all you have to do is find one vertical line that hits it more than once. But in that last example, it was harder to show that it is a function, because I have to think of all possible vertical lines. Like, just because one of them intersects only once, that doesn't mean it's a function. It has to be every possible vertical line you can think of only intersects once. That's kind of harder to prove that it is a function rather than it's not a function. Alright, we got one more there. Let's look at that circle guy. So to tell if that's a function, I'm going to look at just some vertical line and see if it intersects it more than once. I mean, if you think about this one, this vertical line intersects it 0 times. So far, it's not a big deal. This vertical line would intersect it 1 time. So far, so good. But any vertical line that goes through the circle, it intersects it twice, right? One at the top of the circle, one at the bottom. So since I found one vertical line that intersects it more than once, it's not a function. Not a function. There is, you don't have to explain it, but just in case you're looking back at the notes later and you forget why is this not a function? There is a vertical line that intersects more than once. Yeah, okay. Sounds good. Alright, that's kind of all the weird stuff for this section. The rest of it's more bringing it back to math and calculations and kind of normal stuff we're used to. Alright, so let's see. This one, it's kind of hard to get used to too. This is kind of weird, but this is probably the most important, I'd say, yeah, most important topic in this chapter. So getting used to this is good. We won't use this very often, but you'll definitely see this in your next math class. Okay, so it's called function notation. So it kind of comes from, instead of me saying, okay, I've got y equals mx plus b, I can write f of x equals mx plus b. And I know that sounds crazy, but so think of it as y equals, let's say an actual example, like just to get the hang of it, how about 2x minus 5? So you know what, I think some mathematician was thinking, alright, this is the equation of a line, and remember to graph this line, you can make a little table of values and, choose a value of x, let's say 0 or something. But you know what, I think it's misleading because if you look at this equation here, it has two variables, y and x. So it kind of seems deceivingly like you have kind of 2 degrees of freedom, like y could be whatever it wants, x could be whatever it wants. But you know what, once you let x be something, like what if I let x equal 0, like we said? Then am I able to say what y is? Like, oh, well, I want x to equal 0, but I want y to be 500. No, you can't, because y, notice it's already predetermined for you. Once you put 0 for x, y is already determined. So I think that's kind of the thing, y, it's a function of x. That's what they're thinking. Whatever x is, y is already determined by that value. So you don't really have 2 degrees of freedom. You can't say what x is, you can't say what y is. All you can really say is what x is, and then y falls apart from there. So that's the notation they came up with is really because of this. It's a function of x. So they say it's a f of x. That's even how they say it out loud. F of x. That's how you would read that. So like instead of writing y equals 2x minus 5, we say, all right, let me not pretend like I can say what y is. I can't tell you what y is. Y is already predetermined by x. So I'm just going to say this guy y is a function of x. And it's just purely notational. This doesn't mean f times x. You're not multiplying f times x. It's just saying this y is a function of x. So it's almost like you just called y, I don't know, what's a good name? Bob. Bob is 2x minus 5. You say, I don't like this y anymore. I'm going to call it something else. Let's call it Bob. That doesn't mean you're multiplying b times o times b, right? That just means that's his name, alright? Don't try to do math with it. That's kind of what we got going on here. F parentheses x, that's just the name of this function. You're not multiplying f times x. It's just part of the name. I know the Bob thing was kind of ridiculous, right? Sorry. But still, just think of it as a name. You're not going to, If I took your first name and then I tried to do math with it, you'd say, what the heck are you doing? Why are you so weird? It's just a name, hello. It's not a math thing. So even though we're talking about math, it's still thinking of that guy as just a name, f of x. Alright, and the reason that's kind of useful is because, like it says here on the second line, the reason that's useful is because instead of saying find y when x is 3, I think mathematicians got kind of tired of that. They're like, you know what, we're lazy. Because what if I said find y when x is 3? And now I want you to find y when x is negative 5. I don't have to keep saying that long sentence. That's kind of a long direction. Find y when x is bleh. Find y when x is bleh. So now they have a faster way of doing it. They say find f with 3 in the parentheses. So these two things in the green boxes really mean the same thing. So when they say find f parentheses 3, they're saying find y when x is 3. That notation is hard to get used to, but these last two examples in this section are trying to get us to be a little more comfortable with that notation. And then I think, like I said, that'll make your next class, when you go back to this chapter, a lot easier. Alright, so let's look at this function we have here. They gave us in this example 4, f of x equals negative 3/5 x plus 1. Okay. So remember that you're thinking of f of x as y, so imagine that's a y. It's like y equals mx plus b. So it looks a lot like the equation of a line. It's just the f of x is kind of a strange new concept for us. So if f of x equals that, so now what they want is f of 0, that was what they said here. And then they want f of 5, that was the second thing they're asking for. And then f of negative 10, and the last one f of 1. But remember, just basically whatever number's in the parentheses, you're replacing x with that number. So if I want f of 0, I'm just going to replace x with 0, and basically on the right side of this function, whatever's f of x is equal to, you're going to rewrite that guy. And then for the f of 5, I'll do the same thing, but I'm replacing x with 5. x with 5, and then, you know, on and on. The next one, for f of negative 10, I'm going to replace x with negative 10. The last guy, I'm replacing x with 1. There we go. Okay, and then I'll be done. So you know what you could even do, just because I know I'm trying to find what this function is equal to for 4 different values of x. I'm going to write this function with x missing every time, because all these problems are kind of going the same way. Negative 3/5 times something plus 1. The second one's going to be the exact same thing, it's just the x is going to change. So it's still negative 3/5 times something plus 1. And so is this guy. Yeah, it's just whatever was in the parentheses, that's what you're replacing. So the first guy had a 0, that means 0 is going for x. And then I'll simplify that to see what it is. The next guy, I'm putting a 5 in there, so 5 will go there next to the 3/5. The second to the last one, I'm replacing x with negative 10, so he'll go there. And the last guy, I'm replacing x with 1. And then now all I have to do is simplify each one and see what I get. So this first one, negative 3/5 times 0. Everything times 0 is 0. So it's really 0 plus 1, which is 1. Alright, so that, if you wanted to kind of sum that up, you could say f of 0, which is what they asked for, is 1. That's kind of a way to sum it up, because they asked us for the left side, f of 0, and we got 1 as an answer. Alright, let's try this next one here. We're going to multiply negative 3/5 times 5. That's a fraction times a whole number, so I better put that whole number over 1. And I noticed those 5s reduced right away. So really you're just left with the negative 3, and then the plus 1 that was kind of here to the right of it. So it's negative 3 plus 1, which is negative 2. Alright, if you wanted to write that out, that would mean f of 5, because that's what they asked for, is negative 2. Alright, I think we're getting the hang of this. Now, the next guy, you're multiplying, kind of similarly, I have a fraction times a whole number. It's just the whole number now is negative 10. So I'll put that negative 10 over 1 and reduce a little bit. 5 can go into 10 twice. But notice that's a negative times a negative. It's a negative 3 times a negative 2. That's a positive 6, plus the 1 that was kind of hanging out there. 6 plus 1 is 7. Alright, that means if you want to write it out, f of negative 10, that's what they asked for, is 7. Alright, we got one more here, and then I think we're sort of getting the hang of it. We'll try one more, and then that should probably kind of make it a lot more concrete. Let's see, now, this time we're multiplying negative 5/3 by 1. I'm going to put that 1 over 1. This time, though, unfortunately, notice nothing cancels. 5 and 1 have nothing in common. 3 and 1 have nothing in common. Alright, so I'm really going to have to just multiply that, like, numerator times numerator. 3 times 1 is 3. 5 times 1, denominator times denominator is 5. I've got a fraction plus a whole number. I'm going to have to get a common denominator here. Put this guy over 1. The common denominator would be 5, so I'll multiply the second guy by 5 over 5. So I'll keep the first fraction the same, negative 3/5. But now my second fraction becomes 5 over 5. Negative 3/5 plus 5/5. Really, you're doing negative 3 plus 5, that's 2/5. Alright, so if I want to sum that one up, that would mean f of 1 is 2/5. There it is, beautiful. So it's kind of a strange concept, right? But that's really all it means. Whatever number you see in the parentheses is the number you want to replace x with. That's really as simple as it gets. Let's try this last one, and then I think it should sink in. Now they're giving us a new function, and notice they're not saying f of x is blah. Now they're saying g of x is something else. So notice it was f of x, f for function, and now they're going to the next letter of the alphabet after f is g. So see that a lot. If they called one function something, like in the last example, f of x was one thing, well, they're saying, well, you know what, this is a new function, I'm going to call it something else. How about g? And usually that's what they'll do. If they used f of x already, they'll just say, alright, what's the next letter of the alphabet? G. If they already used f and g, the next guy would be h of x. You know, they'll probably just go through the alphabet like that if they have a bunch of functions. But it really means the same thing. I think they just want different names. Like if this guy's name is Fred, for F for Fred, this guy's maybe George, G for George. They're two different guys, you know, don't call them the same thing. That's kind of mean. They're individuals, okay? They're different. Alright, but there's our function, but this time they want us to find g of 3. Alright, I'm going to think about that. G of 3. And then they want g of 0. Okay, fine. And then g of negative 2. Okay. But it's kind of the same thing as the last one. G of 3, that means you're replacing x with 3. It's as easy, yeah, it's just really that simple. So we'll do that, and we're really just talking about the right side of this function. G of x equals, whatever it's equal to, you're going to take, and this one happens to have two x's, it's x squared, and then an x at the end. We're going to replace both of them with 3 there. The next guy, we want g of 0, we're going to replace x with 0. So it's going to be 3 times 0 squared minus 4 times 0, just copying exactly what the function looked like. And then the last guy, they want g of negative 2. So we're going to replace x with negative 2. So it'll be 3 times negative 2 squared minus 4 times negative 2. Alright, let's see. So 3 is the x value in the first one. I'm going to replace both x values with 3. 0 is the x value in the second one. I'm going to replace both x values with 0. And then negative 2 is the x value in the third one. We're going to replace both x values with negative 2. And we'll simplify each one individually, just see what happens. Alright, so this one, I got to be careful because it's 3 times 3 squared. Remember, you have to do exponent before you multiply, so I better leave the 3 outside the same and square the 3 first. 3 times 3 is 9, so that's 9. Here we can multiply those guys. Minus 4 times 3 is 12. Alright, so that's 3 times 9, that's 27, and then you're subtracting 12, that's going to be 15, right? There we go. So if you want to write that out, you could say that g of 3, which is what they were asking for there, is 15. Alright, then the next one we got 0 squared, that's 0, minus 0 times 4, which is 0. 3 times 0 is 0. There's a lot of zeros here. 0 minus 0 is 0. Alright, that means that g of 0, which is what they were asking for, is 0. Interesting. Okay. Let's see here. So the last one here, you got negative 2 squared. Well, that's negative 2 times negative 2, that's positive 4. And then you got negative 4 times negative 2, that's positive 8. So it's 12, because 4 times 3 is 12, plus 8, that's 20. That means g of negative 2 is 20. There we go. Alright. That's kind of it for this section, but I think especially if you're going to be taking the next math class, I just wanted to kind of, at the very end here, just throw this in for fun. It might make the concept a little easier later. So, because we were talking about functions, remember function above, we were saying it's like a correspondence, it's a map, it sends x's to y's. Even though this example and the previous one we're using function notation, it seems kind of like it has nothing to do with that stuff where it's a map and you're sending one thing to another. It's still very similar. So you know what I like to do is think of a function as like a machine in a factory. Machine in a factory. You know, so even in this example that we had above, g of x is our function. So let's say I'm going to really draw a really simple looking machine. Machines are usually a lot more complicated than this, but just pretend. So here's a machine that's got a conveyor belt going in. I don't know, something like this. Here he is. Da-da-da-da. So let's say this is going in, like this conveyor belt is going this direction, and then it's coming out the other direction. And this machine, I don't know what it's doing to the things going in. It's like, I don't know if these are toys, maybe there's like a little action figure or a Barbie that goes in and it puts clothes on him or it puts the hair on or something. But just think of this machine as your function, g of x. So g of x, what was our g of x in this example? It was, it was 3x squared, minus 4x. That was what we had. So I guess, let's see, first they asked us to find, remember, g of 3, they said. So it's like, think of the x value as 3. X values are going in, and y values are popping out. So 3 went in, remember, we put a 3 into this function, what did we get? G of 3 was 15, so 15 popped out when 3 went in. So this machine here, it did something to that number. It took the number 3, it took it, squared it, multiplied by 3, subtracted 4 times that number. It did all these things, and the 15 popped out. And then the next number they asked us to put in there was a 0. So let's say 0 goes in the machine. What popped out? A 0. This function, it did all the things it's supposed to do. It squared the number, it multiplied by 3, it subtracted 4 times the number, and still 0 came out the other side. And then the last one we were trying to find was negative 2. We said, okay, what if we put a negative 2 in here? Well, g of x did the same thing. It did all the operations, and 20 popped out in the end. So So that's kind of connects the topics. So think of a function, even though it's like, just looks like something that we're plugging things into. Just think of it as a machine. It's taking in x values and it's popping out y values for you. But you notice it's doing the same thing to every number. It squares it multiplies by 3, and then it subtracts 4 times the number. Doesn't matter what number comes in, it's doing the same thing to it and then spitting it out the other side. So remember that way. X values go in, y values come out, and depending on the function, it does different things to them. But that's kind of the basic idea. So I know this concept is very strange, but like I said, we know it's going to be strange, and that's why we introduce it early in this class. And that way, maybe in your next class, it'll be a little more concrete and it'll make a little more sense, hopefully. But now we're going to move back. We're going back to the previous chapter, which is more the material from our class, kind of what we're more interested in. Okay, so I'll see you in the next one. Thanks for listening. Have a nice day.